Alright, we are looking at the third part of this AB sample test number 2, the multiple choice, the last part of the non-calculator. Let's go ahead and jump right into it. It actually said it started at 18, but I'm going to be starting at 19 because I did 18 in the last one. As I'm looking at this integral, it's asking me to take an antiderivative, and I see secant squared x and I see tangent squared x. Well, there's a lot of things that there's a lot of things you could do to work your way through this. But the one that I start to notice is I see a secant squared x and I see a tangent squared x. And I know that one of those has a relationship with the other, as far as one has a derivative residual piece of the other. And we know that the derivative of tangent of x is equal to secant squared x. And we also know that the derivative of secant x is equal to secant x tangent x. So if I were to do that, let's say I'm going to actually do the wrong one first, or not the wrong one, but the one that makes it a little more messy anyways. Let's say that I was to do a u substitution with u equals secant x. Then du is going to be secant x tangent x. And if I were to do that, I would have a leftover tangent x because I'd have a u out of one of these, then combine one of the secant x's with the others. That would give me my du, but then I'd still have a tangent x left over. So I'd have to do some more sloppy kind of substitution using this relationship here. Well, let's not do that. Let's try the other substitution, see if that's a little bit cleaner. It will be, but let's see how it would play out. If I were to say that u equals tangent of x, well then du is secant squared x dx. In that case, right here, I have u squared. And the secant squared x dx, that's this other piece, that's going to be my du. So now I'm changing this to the integral of u squared du. Well, that's pretty easy. The antiderivative of u squared is just u cubed over 3 plus c. In this case, u happens to be tangent x, so it's going to be tangent cubed x over 3 plus c. The thing that's closest to that, the simplified version of that, would be a right here, 1/3 tangent cubed x plus c. Still moving forward here, we see that for the absolute value of x is less than 1, the derivative of this. Why would they even need to say this? It's so that this function actually exists. We're looking at just the interval on which it is differentiable. So we're taking the derivative over here. Well, we know that if we have y equals natural log of u, then y prime is going to be u prime over u. Well, I can actually make this a little bit easier for myself. If I know that y equals natural log of 1 minus x squared to the 1/2 power, my pen's slowing down a little bit here. My computer's tired, it's been working hard. 1/2 power, there we go. I can take this power, move it out front, then I don't have to deal with that power in the derivative. So that means that y really equals 1/2 natural log of 1 minus x squared. Given that information there, I can now take the derivative. Well, that tells me that u would actually be my 1 minus x squared, and my du would then be negative 2x dx. So y prime is going to equal 1/2 du, or u prime, so negative 2x dx on top, or just negative 2x, over 1 minus x squared. Some of these things simplify. The 2 and the 2 on top and bottom reduce, and we're just left with negative 1. So y prime really equals negative 1 over 1 minus x squared. Now as I look at that, and I'm trying to see which ones are the closest as far as matching that value, there's not one that seems to, oh, there's an x here, by the way, negative 1x. I noticed that it looks like it'd either be A or B. Well, if I again do that trick where I multiply the top and the bottom by a negative 1, that's going to flip things around. On top, that's going to give me x, and on bottom, I'm going to have x squared minus 1. That means that the answer would actually be B. 21. Ooh. It's always these simple ones that make us think. A function whose derivative is a constant multiple of itself. So that's saying that the derivative, let's say our function is y equals some function of x, then the derivative dy dx is equal to that original function times some constant. Now a lot of times that constant's actually written in front, so let's go to put that in front here. Well, this is something where we've done differential equations to kind of work this out, and eventually we'll see what kind of function it matches. So if we separate the variables both sides, we'll have dy over y equals k dx. And then we integrate both sides, we get natural log of y equals kx plus c. And then we raise both sides as a power with a base e. That's going to give us y equals c times e to the kx. This is an exponential function. And no matter what happens, whenever you start with this derivative equals a constant times the original function, you're always going to wind up with some type of exponential function. Okay, let's look at the next one. For what are the values of x which the graph is concave downward? When we're talking about concavity, that's telling me that the second derivative is less than 0. It's negative. The second derivative is negative. So I got to find y prime, and then I got to find y double prime. So y prime is going to be 3x squared minus 12x. Then the second derivative is going to be 6x to the first power minus 12. So when I'm looking at this, I need to do some charting here. And I need to figure out when does this equal 0, and then find out when is it positive and negative around that. So if I look at 0 equals 6x minus 12, then that's going to tell me that x, if I move 12 over here, 12 equals 6x, x equals 2. So that's my split. That means that 2 is in the middle, and concavity is 0 here, or not necessarily 0, but it changes. So I need to pick something below 2, like 1, and something above 2, like 3. And I need to compare what the second derivative is, and that's going to tell me the first derivative, or the first original function, whether it's going to be concave up or concave down. So this is 0 here. Let's see what it is at 1. If I plug in 1, 6 times 1 is 6 minus 12 is a negative number. So that means this is concave down. And just to double check, if I were to plug in 3, 6 times 3 is positive, 18 minus 12, that's a positive number. So this is concave up. So that means before 2, it is concave down. That means that our answer is C. If x is less than 2, the second derivative is negative, therefore making the graph concave down. Alright, now let's talk about some problem-solving strategies here. As I'm reading this, I immediately notice something here. It says the edge of a cube, so that's some type of measure, is increasing at a rate. If you ever hear the phrase, some measure who cares what kind of measure it is, an area, volume, an edge, a side, a length, is increasing or decreasing at some type of rate, then we immediately jump to related rates. That prompt tells us that we're going to be dealing with related rates. So the edge of a cube is increasing at a rate of 0.05 centimeters per second. So let's give ourselves a cube here, and maybe that'll help us visualize what we're looking at. So we got a square, another square, it looks about the same. Connect it. And each side of the cube, it says, is S. So that's S, that's S, that's S. Those aren't fives, those are S's. I hate it when they use S's because it looks like a 5. And especially using a 5 here, what are they thinking? Alright, now let's see what the question is asking us. It's asking us about the change, the rate of change of the volume, the rate of change of the volume, the rate of change of the volume over time. So it's asking us, what is dV dt? Well, we know ds dt. We know these sides are changing 0.05 centimeters per second. And then we know that the volume of this cube, just because we know our geometry, the volume is S cubed. Using this equation, I can relate all these pieces together. So now all I need to do is take the derivative. The derivative of this equation is going to give me dV dt on the left and 3s squared ds dt on the right. Well, it's not just 3s squared like E, because ds dt has to be multiplied in there. So that's going to become 3s squared times 0.05. 3 times 0.05 is actually 0.15 s squared. So that's my dV dt. I took the derivative with respect to time. I multiplied in this chain here, the ds dt, that's the derivative of the inside, which is the s. And that gave me the simplified expression of 0.15 s squared. D is my answer. The tangent line to the graph here, at this point here, intersects both coordinate axes. What is the area of the triangle formed by the tangent line? Oh, this has got a lot of stuff going on in it. Well, let's start by taking the derivative and evaluating the slope and figuring out this actual line. We know that the equation for a tangent line is just the old school point-slope form. We've translated this somewhat, and we've considered it now to be y minus f of a is equal to f prime of a times x minus a. And in this case, f of a equals e, and a equals 1. So we just need to figure out what f prime of a equals, because they gave us the x and the y value here, the a and the f of a. So what does f prime of a equal? Well, let's figure that out. We know that y equals e to the 2 minus x, then y prime is going to become e to the 2 minus x times the derivative, the chain of this top piece, which is negative 1. So if I were to plug in e for my x, because that's what e is here, this is going to become e to the 2 minus e times negative 1. Now I can simplify that a little bit, because anytime I have a function, or not even a function, just a base, let's call it z for no apparent reason, to the a minus b, that's the same thing as z to the a over z to the b. So what does that tell me? That means that I have e squared over e to the e, and this is negative. That's pretty intense there. So what I need to figure out is when does this intersect both axes? In other words, I'm trying to find the x and y intercepts. That's what I'm trying to find. So let's start by giving myself an x and y axis to work with. So I can maybe sketch this out a little bit. Ooh, I did something very horrible here. I said that I need to plug in e. I'm not plugging in e. I'm plugging in 1. So much easier. E to the 2 minus 1, which is really negative e. So that means my tangent line is going to become y minus e equals negative e times x minus 1. If I were to simplify this, I'd have y equals, and over here we have negative e to the x, or negative e times x, plus e, and we got another plus e over here, so we have negative ex plus 2e equals y. Well, that tells me something here. That tells me that my y-intercept is at 2e. My x-intercept is what I would get when y equals 0. So if I set that equal to 0 and solve, then I have negative e times x plus 2e. That gives me e times x equals 2e. Divide both sides by e. So I know that x is going to be 2. So that gives me my line connecting these 2 points here. And I'm trying to find this shaded region. It's colored in green. Well, that's pretty easy, actually, if you think about it. It's just a triangle. And area of triangle equals half base times height. So it's going to be half 2e times 2, which is really 2e. The answer is A. It's a pretty intense problem-solving deal there. How do we go about doing that? Well, we had to find the tangent line. We had to find when that tangent line intersected both the x and the y axis, and then use that information to find the area of the triangle created by that region with some simple geometry. Alright, we got a couple more here. 3 more, in fact. Something's missing from this equation. It got a little cut off. This should be a 7, 5x to the 7. So we have, if f is the function, 5x to the 7 over 7 plus 4x to the 6 plus 6x to the 5th plus x plus 1, what are all the x-coordinates of the points of inflection? Remember, the x-coordinates of the points of inflection are when concavity changes. And concavity changes when f double prime of x changes sign, either positive to negative or negative to positive. So we need to look at second derivative and see when that changes sign. So let's take a look at the second derivative. If we look at f prime of x, the first derivative, that's going to give us 7 times 5x to the 6th over 7. Those 7's are going to reduce. Plus 6 times 4x to the 5th plus 30 times x to the 4th plus 1. This winds up, if I simplify this a little more, we got 5x to the 6th plus 24x to the 5th plus 30x to the fourth plus 1. So we got to keep going. Now second derivative is going to give me 30x to the fifth. Excuse me. 5 times 24 is 120, x to the fourth. And 4 times 30 is also 120. This one's x to the third, and the derivative of, this is the second derivative, by the way. The derivative of 1 is 0. So now we got some factoring. I can pull out a 30x cubed. I'll be left with x squared plus 4x plus 4. And if I were to factor that even further, I'd have x plus 2, x plus 2, and 30x cubed. So potential places where concavity might change is the areas where this would equal 0. This is a polynomial, so I know it's continuous the entire time and differentiable. And I know that I'm only looking for when it equals 0, not for when it does not exist, because it always exists. It's a polynomial. So let's do that. Let's chart this out. We know that x could equal 0 or negative 2. So I need to look at 0 and negative 2 and the in-between. I'll give myself some charting space here. Let's get some vertical lines. So we need to check in between these as well. And on either side of it. So we know that these values are going to be equal to 0 at those 2 points. We know that it equals 0 here, the f double prime of x equals 0 there, and there as well. We want to check what does it equal at the places in between. So let's look at negative 1. Well, looks like I wrote these backwards. Let's do these again here real quick. So if I rewrite this, I'm looking at negative 2 and 0. So negative 1 isn't going to go there. It'll work for the middle though. So that means I need to look even lower, down to negative 3, and I can go up to 1 for the final one. So I need to plug these into the original, or not original, but the second derivative. So I'm looking at f prime, double prime of negative 3, and I'm looking at f double prime of negative 1, and f double prime of 1. Well, now that I have it factored out, it actually makes it kind of easy to multiply. So in the first one, the cube of a negative is going to be negative. So this one's going to be negative times negative 3 plus 2, that's a negative, and negative 3 plus 2, that's still a negative. So that equals negative. That means we are concave down when we are before x equals negative 2. So the original function, f of x, is concave down here. Let's see what happens at negative 1. Negative 1 cubed is still negative. Negative 1 plus 2 is positive. Negative 1 plus 2 is also positive. That tells me that I'm still concave down. So this point right here is not a point of inflection. It is not, because it did not change concavity. It's concave down. It means it was going down. It almost changed concavity. And then it kept going down. It never actually went up. Actually, that's kind of an inaccurate sketch there. Shouldn't use that one. Let's look at this last one. We know that the first one is going to be positive, and 1 plus 2 is positive, and 1 plus 2 is positive, 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 positive is positive. So it means we are concave up. We have a change. So this is a point of inflection. We changed concavity, therefore, we changed concavity, therefore we have a point of inflection. That change came about at 0. 0 only. Let's look at number 26 is talking about a normal line. They're very specific here, saying that a normal line is perpendicular. That's the key word there, perpendicular to the tangent line. So we basically have to find the tangent slope, but then make it perpendicular. We also need to be aware of that normal line is going to use the same x and y value from the original equation. Let's clear out all these annotations, start from scratch. So let's look at y prime. Y prime, well, if this is x squared minus 1 to the 1/3 power, that means y prime is 1/3 times x squared minus 1 to the negative 2/3 power. And then we have to do the derivative of the inside, which is 2x. So this is going to be kind of sloppy, but we know that we need to plug in 3 for our value. So let's go ahead and do that here. If we have this negative power, that means it's going to flip it down to the bottom. So this is actually 1/3 times x squared minus 1 to the 2/3 power. And then we have times 2x, so we'll go ahead and put that on top. So the simplified version of our derivative would be this. Now we want to evaluate this at x equals 3. So at x equals 3, y prime equals 2 times 3. And on the bottom we have 3 times 9 minus 1 to the 2/3 power, which is really 6/3 times 8 to the 2/3 power. 8 to the 2/3 power means cube root it and then square it. You could do those in either order, but I choose to cube root it first. So cube root of 8 is 2, squared is 4, so this is 6/3 times 4, which is really 1/2. That is our tangent slope. That's not what we want. What we want is the normal slope. The normal slope then is going to be -2. It's the opposite reciprocal of our tangent slope. So that's our normal slope. Now what we need to figure out is we have our x1 equals 3. We have our slope equals -2, and we need to know our y value. In order to find our y value, we plug x back into the original equation. So y1 equals the cubed root of 3 squared minus 1. Well, that's going to be the cubed root of 8, which is 2. So our template is always y minus y1 equals m times x minus x1. y1 in this case is 2, m is -2, and x minus, over here we're going to have, what is x1? x1 is 3. Let's see which one of these is going to match that. Well, it looks like they moved the x's over to the left side and put it in standard form, so let's go ahead and do that. We move the -2 over. So if we distribute this -2, it's going to become -2x plus 6. And then we got y minus 2. If we move the x over to the left and the -2 over to the right, we have y plus 2x equals 8. D would have been our answer. Alright, I'm going to finish with this next one, and then we'll be done for now. Let's scribble this out. There's no answer, it's just an extra piece that's going to distract. Alright, which graph represents the position of a particle, s of t, if we know that the velocity and acceleration are both positive? So they're saying velocity is greater than 0. In other words, that means that it's increasing. They're also saying, or its slope going up. They're also saying that the acceleration is greater than 0, or it's positive, and that means that it's concave up, or that it looks more like a smiley face. So we need something going up and concave up. Oh, I guess the only one that would really match is C. Because it can't go down, and it can't be concave down. So all these type of shapes are out. So concave down is out, decreasing is out. It's got to be C. B is concave down. That's out. A has no concavity, so that's out too. D is concave up, but it's decreasing, so that's out. E is both wrong. It's decreasing and it's concave down. The only answer would have been C. That's it. Have a good night.